So, thank you. Very awkward speaking two opposite directions. So I'm very happy to be here again, been in this place and this room many times, on that side and this side. So my title today is, just talk, you don't see any. My title has three words: knots, units, and modular forms. So these are three topics that are usually very, very separate in mathematics, and I want to show that there are some links between them. All of them are both fairly elementary at the beginning, with the definitions quite advanced eventually. And this audience, I think, is also very mixed. There are some people who are very young, and some people who are almost as old as I am. So I will try to kind of keep a mixed level. And as usual, people think everything is very elementary if they understand it themselves. So I also think that if it's not, and something is not clear, especially young people, please just ask and say, can you say a little more or explain that again or better or in an easier way. Anyway, I want to link these three things, and actually there's another topic that I didn't put in the title because it's even more frightening. This is K-theory, algebraic K-theory. And actually that will be quite a good beginning, but only a somewhat easier version, which I hope I will be able to explain in a more or less elementary way. So the order will also be very different. I'll start with units, and then something about K-theory, and then the knots will come in a little bit later. So we start with a number field. So that means a finite extension of rational numbers. So the degree is some number which is traditionally written R1 plus 2R2. So this means you have R1 real embeddings and 2R2 non-real complex embeddings, or the more elementary level, any number field can be obtained by adding to Q to a single algebraic number which satisfies some polynomial equation which is irreducible over Q. So the degree is the degree of the field, but over the real numbers by Gauss, it splits as by Gauss, every form of the real splits into a finite number of linear forms and a finite number of quadratic functions of second degree, which are irreducible. So there are R1 of these and 2R2 of those. So I mean, for instance, if I have Q squared minus 3, then R1 is 1, there's 0, and R2 is 1. And now, if you have F, you have the ring of integers, which I won't define, I think most people know, and I won't use it. And then this contains the ring UF, which you can also write O of cross. These are the units of F. So this is the set of numbers which belong to X, and they are algebraic integers, which means they satisfy an equation with the integer coefficients and leading coefficient 1, but their inverse is their not zero, their inverse is also an integer. So in the case of Q, this is just plus or minus 1, but usually it's infinite. And the famous theorem of Dirichlet. So let me put equals dot, and I'll use this for convenience during the lecture. When I write between two groups, that it's equal dot and it's up to torsion. So maybe up to things of finite order. I'm not going to be so precise. And then the famous theorem of Dirichlet is that this group is finitely generated. It's a Abelian, and the rank is always given by this famous formula, R1 plus R2 minus 1. So we know the abstract structure of the group of units, but a famous unsolved problem, one of the biggest problems of all of number theory, is actually find these units, or even subgroup of finite index. So given the field, write down R1 plus R2 minus 1 independent units. This is known for some very special class of fields, but in general it's completely hopeless. So one of the things I'll do in this talk, it will look for a moment like I'm answering not only this question, but an even much more general question. I'll be giving units in arbitrary cyclotomic extensions of arbitrary fields. But then if you look more closely, I'm not quite giving units, I'm giving a certain quotient of the group of units. Explicitly, that's very explicit. And it looks like I'm creating units, but that's not possible. I mean, it's not possible for the moment, and probably not for many, many years. Okay, now, I now come to algebraic K theory. So if you have a ring, like OF or F, then there are various groups called algebraic K groups, and for instance, K1 is just a multiplicative group, and so in our case of the field, the multiplicative group for the field, if you just remove 0 of the ring of digits, it's these units, and so that's called K1, and there's a generalization, Kn of OF, and Kn of F, and it's known that if n is bigger than 1, these groups are also are actually the same. So these groups are very different. This is finite rank, this is infinite rank, but for larger n they're the same proportion. And by a wonderful theorem of Borel, one knows the answer. So this is 0 if n is even, I mean up to torsion again. If n is 3, there's a formula for it always is finitely rank, and Borel gives the rank, but I'm only going to talk about n equals 3, so I'll just give the answer in that case. And in that case, instead of R1 plus R2 minus 1, it's just R2. So again, we know this group explicitly, but up to abstract isomorphism, but to construct elements is now much harder. Because for K1, at least we know what the unit is. We don't know how to find them. But for K3, even the definition of algebraic K theory is very abstract. It's some homology group of the limit of some infinite sequence of topological spaces. It's even the definition is very hard. But one knows, thanks to the work of Bloch, and also other people who finally proved everything is part of conjectural. So, Suslin, Levy, various people, I won't write the names, we know that at least again up to torsion, there's an elementary description of this K3. Actually, there's a conjectural elementary description of all of the higher Kn that I found many years ago here in Moscow as a conjecture using the computer, and it's now been partially proved for the cases K5 and K7. Remember, the equals to 0. I worked touch on R for other people. Anyway, I'll only talk about this. And this block group is something elementary. And so I'd like to explain what the block group is, even though it's not completely easy, but it's fairly elementary, so elementary in the books. You couldn't teach this in high school, but it's certainly more elementary than algebraic K theory. So we start with Z of F. So Z of F is formal combinations of numbers x, where x is in the field. And it's just a formal combination. You put it in brackets and you can add or subtract those things. And now I'm going to make a map.
I'm sorry. Yes, the left and right brackets are different.
No, they aren't. They're just one is on the left and one is on the right.
No.
These are also different. I'm sorry, my handwriting
X is
Lower.
lower.
This is also the same, but my handwriting is
No,
not.
I see. Sorry.
Yeah, this is meant to be square brackets. There's no, also the different sizes, but but you know, that's how it is. So I map this thing into the exterior square of the algebraic, of the multiplicative group of the field. I'm only going to do this for fields. And so if x is some element of the field, then here's x. And then this is this space of expressions, a wedge b, I'll always put them in parentheses. And if you're not used to lambda 2, it just means that these are formal expressions with only two properties. One is that it's antisymmetric, and the other is that it's linear in the second variable, and therefore also in the first, because it's antisymmetry. So it's a group. So you can make formal sums, and it's additive in each component, but where the component is in f cross, you have to multiply. So one has to get used to that. I'll give an example in a minute. You'll see it's actually very easy. And in fact, if you take half an hour, you can show this to a good high school student, but not using this notation in a way that they can compute quite happily with it. So what you do is you set x to x wedge 1 minus x. Of course, x should be non-zero, so and also 1 minus x. So I should tell you especially this map will come D. You just decide that 0 and 1 you set to 0. Okay, so that's the map. And now B of f will be the kernel of D divided by some simple elements that you can make in the kernel that I'll explain in 1 minute. But first I want to make this thing clear with f cross. So let's take the example where my field is Q. And since 2 and 3 are very difficult notations that you don't learn until you're 5 years old, let me use simpler notations for 2 and 3. I'll call them alpha and beta. But alpha is the element, beta, and it says an element of this group f cross. So when I write 6, it will be alpha plus beta, because I'm now writing it additive. So now let's take an example. If I take 1/3, so 1/3 in square brackets maps under D to 1/3, wedge 2/3. But 1/3 is the inverse of 3, which is beta, and I'm writing my group additively. So 1/3 becomes minus beta. But 2/3 is 2 divided by 3, so it's alpha minus beta. But now this thing is additive, so this is minus beta wedge alpha plus minus beta wedge minus beta. But something wedge itself is 0. Again, I'm working out the torsion. So this is simply minus beta wedge alpha. But we also have antisymmetry. And so I can also just write alpha wedge beta, because alpha wedge minus beta is the same as plus alpha wedge beta. So that's not 0, because 2 and 3 are not the same, so the wedge product isn't 0. But now if I take 1/9, I do the same thing. Now x is 1/9, 1 minus x is 8/9. So 1/9 is 3 to the power minus 2, so if I write it additively, that's minus 2 beta. 8/9 is 2 cubed divided by 3 squared, so that's 3 alpha minus 2 beta. And again, this symbol is additive, so this is minus 6 times beta wedge alpha, which is 6 alpha wedge beta, plus 4 times beta wedge beta, which is 0. So it's simply 6 times alpha wedge beta, which is again not 0, but it's a multiple of the first one. And so we see that if I take 1/9 minus the 6 of 1/3, then this will be a class, well I haven't yet said what I divide by, this will be a class in the block group of Q. Now you could say I'm not very interested in the block group of Q, because this theorem says it's the same as K3, and K3 is 0, because R2 is 0. And that's true, this element up to torsion will be in the thing that I divide by in a minute, but still it should make clear that it's not very difficult to write down elements in this block group. It's completely explicit. All you have to do is factor some element x at 1 minus x into, say, prime factors in the field, or something like that. Okay, now what do I have to divide by? Well, for that, you have to know so K-theory is a kind of homology. All homology groups, homology or cohomology, you have some map D, and you take things killed by D divided by things in the image of D. So it's called cycles divided by boundaries, or co-cycles by co-boundaries. So here, this kernel of D is some kind of cycles. or cosines. I have to say what the boundaries are. So that means that you always want to look for the quote-unquote trivial way of satisfying that equation. So what's the trivial way? Well, there are several examples. For instance, x plus 1 minus x is certainly the kernel, because under D this maps to x raised 1 minus x plus 1 minus x wedge x, which is certainly 0. And similarly, you can check that x plus 1 over x also maps to 0, at least of proportion. So you can multiply it by 2. So in this group, you can find the inverse of an element by replacing x by 1 minus x or by 1 over x. But those are very boring relations, but there's one nice relation. And so let me write the easiest theorem in mathematics. Of course, that's my personal choice. But I think, so of course there are many easy theorems in mathematics, like 1 plus 2 equals 3, but you can't really call that a theorem. A theorem should have the non-obvious proof, and also should have infinitely many special cases. And so the easiest theorem should be very easy. But it should still be a theorem, it should be surprising. And so I think this one qualifies. Imagine you have a bunch of numbers in a field. It doesn't have to be a number field. So I have a collection of numbers indexed by the integers. So it's a doubly infinite sequence. And then we assume that 1 minus xi, for every number in the sequence, 1 minus that number is the product of the two neighbors. Put them in order. So 1 minus xi is xi minus 1 times xi plus 1. Then, who knows the theorem? That's the hypothesis. What's the theorem? You know, of course. No cheating.
Can you stand aside?
Sorry?
Move over.
Oh, if I move, you'll know. Okay, the theorem is that xi plus 5 is equal to xi for all I. The theory is always 5. It's a very nice fact. And I told you it's the easiest theorem in the world. Well, it really is, because even if you don't like to prove theorems and have no specialness, you have no ability in this direction, you cannot fail to prove this theorem if you simply try. Because you start x1, x2, then the next one, 1 minus x2 is the product of x1 times this, and the next one is 1 minus x2 over x1. Now the next one is 1 minus this divided by x2. So it's becoming more complicated. 1 minus this is that, I divide by x2, it's that. But now a miracle happens. The next time becomes less complicated. Because 1 minus this thing is 1 minus x1 minus x2 plus x1, x2 over x1, x2. But that factors as 1 minus x2 over x1 times 1 minus x1 over x2. So suddenly the next factor is simpler. And now 1 minus this is 1 minus x1 minus x2 over x2. When I divide by that, I get x1. And that's actually already a proof, but if you really want, you can do it once more. 1 minus that divided by that is equal to x2. So that's not a very difficult theorem, but it's really a theorem. You have to discover it. It's a beautiful fact with 1,000 implications, maybe not 1,000, but certainly plenty in different parts of mathematics. So that's where this group comes from, because now, imagine that I have such, I'll call this thing then. Now we know that this sequence is not an infinite sequence, it's a cycle of only 5 numbers, where each number in the cycle is 1 minus the product of its neighbors. So now to this I will associate the sum of xi, I number of 5. And I claim that this thing is certainly in the block group, because let's compute D. So I have to take the same I mod sum, I mod 5, xi, wedge 1 minus xi, but 1 minus xi is xi minus 1 times xi plus 1. But my symbol, remember, is linear. So I can write this as xi wedge xi minus 1 plus xi wedge xi plus 1. But because of the antisymmetry, I can change the order. And so it's the sum xi wedge xi minus 1 minus xi plus 1 wedge xi. But if I runs modulo 5, so does I plus 1. And so these things simply cancel. So that's a very beautiful way to make elements that satisfy this marvelous thing. And that's exactly what we have to divide by. So if I recall, it's very convenient. Many lecture rooms, it's just too high, I can't get it. So here I divide by these 5 terminations. So that's called the block group, and as I say, the theorem is that it's equal to K3, and therefore by Borel is this rank R2. Now, I haven't really motivated where does this 5-term relation come from, and where does the K theory come from, and where does the whole thing come from. So there are two motivations. So one motivation is the so-called dilogarithm. So the usual logarithm we know satisfies the log of AB equals log A plus log B. So the log converts F cross. It converts the multiplicative group into an additive group, which is what we're doing here. But we know by Euler that log of 1 minus x minus log 1 minus x is the sum x to the n over n. So Euler invented the dilogarithm wheel, which also the trilogarithm, so what I want to use. So the dilogarithm is this function. I mean, if x is smaller than 1, an absolute value, say a complex number. And what you find is that if xi is a Fine cycle, so it satisfies this relation in C, then this was already found by Abel and by Spence and by Lobachevsky and by about 5 people discovered it independently. If you add up the dilogarithm is not an elementary function. You cannot express it in terms of log, but this thing is a combination of logs. So there's some complicated, ugly formula, but it tells you that this is roughly the functional equation, just like log AB is log A plus log B. But if you want a good value, then what you should do is take a multiplication. So I'll write it, maybe I should call these Z, right, but they're complex numbers. If you take the modified one, which is the Bloch-Wigner dilogarithm, I won't write that. I'll write the definition, but it's not important for anything I'll do. You take Li2 of Z, but you make two corrections. You throw away the real part, keep the imaginary part. And secondly, you subtract the product of logs, which is log absolute value of Z times the imaginary part of log 1 minus Z. That doesn't important. It's not important, but this function is one value. It takes a unique value even after you extend it to the plane. It's a function defined everywhere, and now the function equation becomes completely clean. And this is only for the complex embeddings. Remember, my number field that I care about has many complex embeddings, but also real embeddings. If you take the real embeddings, then if you have real numbers also forming a 5 cycle, well, of course, the sum of d of xi is still 0, but it's boring because each d is 0. If these are real numbers, the imaginary part is 0. So there's a replacement called the Rhodes logarithm, and the Rhodes logarithm is very simple. It's Li2 of x. I'll just give the formula if x is between 0 and 1, the only case I'll need. This time you subtract a half log x log 1 minus x. And again, it satisfies the 5-term relation, except for one thing. When you compute the sum of the 5 r's for the 5-term relation, you don't get 1, you get plus or minus pi squared over 2. And so you actually, this thing takes values on a circle. And the circle has length pi squared over 2. So this is an invariant that you can only use for finding torsion. But still you can use it. So as an example, if I take my example before, remember 1/9 is a formal element plus 6 times the third. So if I apply this r to it, then I take r of a 9th plus 6 times r of a third, and when you compute this on a computer, or exactly in this case you can prove it, you get minus pi squared over 3, which is the rational multiple of pi squared over 2, which is what I was telling you, that this whole group is torsion, and therefore any given element has to go to a rational multiple of pi squared over 2. So that's one motivation where this function equation comes from. This function equation was discovered, I think, in 1827 for the dilogarithm. So this 5-term equation is very old. But there's another motivation, which is now going to lead to the part about knots and 3-dimensional topology, which is the following. I'm going to look at hyperbolic 3-dimensional manifolds. I put hyperbolic in parentheses because actually we know by Thurston, not by Perelman, that most manifolds in some reasonable sense are or can be expressed in terms of hyperbolic 3 manifolds. So I'm not going to go into detail at all, but such a manifold can be triangulated like any manifold. So here it becomes a union of a finite union of some triangles, but they are triangles that are now tetrahedra, because it's three-dimensional. But these are ideal tetrahedra, so this is in hyperbolic space. Hyperbolic space is like the upper half plane. I think you've all seen this upper half three-dimensional space. So if you want to draw it with, and I want the four vertices to be at infinity. So if I draw it in that model, then the upper half space is C cross R plus. R plus goes out that way. So then the boundary triangles, maybe three of them I put on this thing and one at infinity to make it easier to draw. Then it will look something like that. But I'll just draw it as a straight tetrahedron. You can do that with some other model. So now such a thing has a volume, because there's a volume form here. I'm not going to define it, it's very standard. And the volume of this tetrahedra only depends on its four edges, because what I should tell you is this is one dimension too low, but if you imagine, no, sorry, it's the right dimension. You can also identify the hyperbolic three space with the interior of the unit circle. So you can think of the unit circle, which is P1 of C, C plus the point of infinity. You can think of this as the boundary of three space. And so these 4 points here have a cross ratio. So I'll put R delta is the cross ratio of the Zi. So again, I think most of you have seen the cross ratio Z1 minus Z2 divided by Z3 minus Z4 divided by delta 1. But what's more to the point, you can move by applying an element of GL2C or PGL2C, 2 by 2 matrices, to your element in C. You can change. So you send every Zi, the whole thing, the whole space, AC plus B over CC plus B. And then when you do that, the cross ratio is invariant, and it's well known that you can put 3 of the points at 0, 1, and infinity, and then the fourth one, let's call that C. This will be the cross ratio, since it's invariant. So you can think of the cross ratio as some formula, or you can put 3 points at 0, 1, infinity. So that's the only invariant, because you can always move this. And so therefore, this volume must be a function of Z, of this cross ratio, and it is in fact exactly the Bloch-Wiener diagram. It's a formula due to Lobachevsky, who had a much more complicated way of stating it, and Milner found this very smooth way of giving it. So that's the volume, and now the 5-term relation is easy. Think in 3 dimensions. If I draw, 2 dimensions, if I draw this picture, it looks like a tetrahedron, but imagine I'm looking from above, I flatten it down. What I see is it's flattened in the plane. It consists of these 2 triangles minus these 2 triangles, and the total area is 0, everything cancels. So the same is true in 5. If I have 5 points in P1, then if I take any 4 of them, so I leave out 1 of them, and take the volume of the delta with those vertices, well, actually it's the alternating volume with some orientation, you get 0 for the same reason as in this picture, the alternating sum of the areas of the triangles is 0. But because I told you that each of these volumes is a dilogram, that's a sum of 5 dilograms. So therefore, we're actually very close to hyperbolic geometry. And what this shows you is that you're the source. These hyperbolic free manifolds are the source of elements in K-theory or in the block group. Because if you take your manifold and you triangulate, then these delta i's are not just independent things. The fact that they fit together into a closed manifold, if you compute, exactly means that the sum of D of these cross ratios will be 0. So we're in the block group. And if I change the triangulation, one knows that you can go to any triangulation, from any triangulation of 3 manifold to another one by taking 2 neighboring simplices, tetrahedron, they have 1 triangle in common. You remove that triangle, you put the line between the edges, and you break that up into 3 more tetrahedron. It's called 2-3 Popper rule. But that 2 and 3 is exactly the 5 of this relation. So going from any triangulation to another is just applying this 5-term relation. And so if M, again, is triangulated, as the disjoint union of some triangles delta I, then if you take the sum of the cross ratios, you don't add them as numbers, you add them as formal elements in Z of C, but actually it's only some number field by rigidity theorem. Well, then you get an element So let's call this element xi n. This element is a well-defined element in my log group, because if I change the triangulation, I change exactly two triangles, become 3 triangles, 2 plus 3 is 5, I'm just changing like this 5-term rule. If you're seeing this the whole time, I don't expect every word to be clear, but at least roughly how it goes.
How do you get a number field from a 3-manifold?
Sorry?
How do you get a number field from a 3-manifold?
Well, that's a very good question. Actually, I'm trying to give a weaker answer, but it strikes me I can simply give the answer in this case. To say that the manifold is hyperbolic, well, one way would be if you had hyperbolic means it locally looks like hyperbolic space. So it's a metric of constant negative curvature minus 1. But actually it's a theorem because of rigidity, it's globally a quotient. And what's more, the rigidity tells you that this group gamma is the subgroup of the same DGL2C we had before, is unique up to conjugacy, of course. So since it's unique up to conjugacy, the traces of its elements are unique. But since this manifold is, let's say, compact or finite volume, it's finitely generated. So by taking the traces of the gamma, I only need finitely many. And so the corresponding manifold, number field, thank you very much for the question, in fact. You take all gamma and gamma, it's enough by some simple identity to take a set of generators. And so that's a finite list of algebraic numbers. And that's like, that is very explicit. There's a standard software you can find on the internet called Snap. You type it in, you draw a picture of a knot, and it will immediately describe everything, including the number field and the element A. So this looks a little abstract, it's very computational, it's very explicit. Okay, now I have to come to some content. So that was one source. But now I want to bring in the last word of my Bible. At the moment, I think I shouldn't use the outside words, because I think if you're here, you can't see that one. And if you're there, you can't see this one. And if everyone had been smart enough to sit in the middle, I could have used them all, but we weren't, but I wasn't, so. Okay, so I will therefore erase. This is this. So now I want to bring in the third element, but I won't start with multiple functions. I want to start, since this is the colloquium talk, I feel that every colloquium talk, but I can only do it in this one, the speaker should give you two things. The simplest theorem in mathematics, I already did that, and the most beautiful formula in mathematics. So I'll give you that. I've given it in this room before, and many of you know it anyway. This is not specially my choice. Many people say that this is the most beautiful formula, except it's only people who can't count because it's a pair of formulas. So it's the two most beautiful formulas in mathematics. And it's called the Rogers, I'll write again, just Rogers and Ramanujan. Maybe I won't write it out, it's too long. Rogers-Ramanujan identities. So they're called by both names. They were discovered by Ramanujan around 1915. And then somebody told them that Rogers found them 8 years earlier, but Rogers was less famous. And then they met and they wrote another paper with the third proof. They had completely different methods. And then they also wrote a joint paper. So it's actually Ramanujan, Rogers. Anyway, and I think there are now 550 proofs. So these identities involve a letter which should be X, but it's traditionally always called Q. And the identities are the following. You have two functions which are traditionally called G of Q and H of Q. So I'll give the definition and then the formula is a formula for them. So the first one is the sum, Q to the n squared over Q in parentheses n. So Qn is called the Qn factorial, or the Pochhammer symbol. It's simply notation for 1 minus Q times 1 minus Q squared up to 1 minus Q here. So this G is 1 plus Q over 1 minus Q plus Q to the fourth over 1 minus Q times 1 minus Q squared. This certainly converges if Q is less than 1, but it also converges as a formal power series. You just expand this. So you get your Q, Q squared, Q cubed, Q to the fourth, but when you run it Q to the fourth, you'll get another Q to the fourth, Q2 Q to the fourth, and so on. And now the discovery is you can take this power series, and like any power series in the world, you can write it as a product of certain terms, 1 minus Q to the I, to some power, or if you prefer writing power in the denominator, with the minus sign, you can put 1 over 1 minus Q to the I. And so here the formula is very beautiful. It's the sum, first write it the way number theorists might, It's the sum, it's the product. So I have 1 over 1 minus q to the I, where I, the genre symbol of I over 5 is minus 1. If you aren't a friend of the genre symbol, I can just say I is congruent to either 1 or 4, not 5. And the other one is very similar, but here you put q to the n squared plus n, so n minus n plus 1 over qn. And this one is the product where I over 5 is minus 1, so it means I is congruent to 2 or 3, not 5. Same thing. So those are these very famous, very beautiful identities. For one reason, people think it's beautiful, but they're very short and sweet, but also they're surprising because you suddenly these 5 counts that you don't see anywhere on the left. But actually, the important part of this function is not these explicit formulas, but because of a formula found much earlier, 100 years earlier by Jacobi, this means that G and H almost are modular functions. So first, let me say that the almost means you actually have to multiply here by a power of q. You have to take exactly q to the minus 1/60th and q to the 11 over 60. And so now what do I mean by modular function? Well, I can write it. Let me make a vector valued function. Z is now a point in the upper half. So that means the imaginary part of Z is positive. And then in the theory of modular forms, which I haven't yet come to, one always writes q to be e to the 2 pi I z. And so q then, because z is in the upper half plane, q is in the universe. And so now let me take these two functions, but I want a vector valued function to make it more beautiful. So I'm going to take both components of the Rhodes-Ramanujan identities as the two components of the vector. So this is a function from the upper half plane in C2. Now, it has a trivial transformation property. If you replace z by z plus 1, then of course you don't change q. So you also don't change g of q. But you do change q to the minus 160, because that really means e to the 2 pi I times minus the 60th of z. So you will change that by a factor zeta 60 inverse, where I'll always use the notation zeta n for the standard n from 0. And similarly here, you'll have zeta 60 to the 11. So this is a trivial fact, and it has nothing to do with Rhodes-Ramanujan. If I took any 2 power series g and h and put these numbers at random, I would always have this. But now the remarkable thing is that there's a second transformation law, which I had in my notes, but I'm too lazy to look up. So I'll invent it, and I may get the 2's in the wrong place. So it's something like sine pi over, I'll put sine 2 pi over 5, 2's are the articles. I think it's this matrix, or else the other one. Anyway, it's some matrix with coefficients that are constant. There's no z, and then here, it's g of z. So the beautiful fact is that this vector valued function, sorry, what can I call it, tau instead of z, this function is invariant up to a factor which here is a matrix and not a number, but still it's constant. This thing is invariant under z goes to z plus 1 and z goes to minus 1 over z. But I think everybody has seen that that's the same. The group generated in these two transformations is the group SL2Z of 2 by 2 matrices with integer entries and determinant 1, and such a matrix acts like the famous Merkel's fractional linear transformation, like this. So the special case here, z plus 1, is this matrix, 1, 1, 0, 1. Determinant 1, this one is 0, minus 1, 1, 0. And those two generate this group. And so this together tells you that actually I can forget these two special cases and deduce from them that if I take gamma z for any gamma SL2z, that's up to a matrix depending on gamma but not on z, you will have such a transformation. And that's called modularity. So that's the word modular form, in this case modular function, of my title. Okay, so that seems to have nothing to do with the other. But now I want to make a link due to Werner Nahm to the decay theory and to this strange definition that I motivated a little by showing you that a free manifold will give in a canonical way elements belonging to this block group. But there's another classical way which was discovered only a few years ago by Werner Nahm, and it's very simple. So let me say what he discovered, his conjecture. So we just saw the two Robinson-Newton functions, and they each have the form q to a quadratic function of n, and then we have this n factorial. So then we generalize it. So this is Werner Naum, a mathematical physicist, German, in Dublin for many years, and he made a generalization. For the moment, that if you're taking notes, this is going to be temporary. A, B, and C are going to be rational numbers, and A will be positive. And now you replace q to the n squared by an squared plus bn plus c. It turns out to be more convenient to put an squared over 2, because this is what we need. So now, what we just showed is that if A, B, C...
Sorry, 1/2 of only first term of...
I can't hear you. What?
1/2 of...
Yeah, of course. Well, I mean, 2 factorial, 1 factorial, and 0 factorial. If you want to be the only person. Like the usual way of writing sums with factorials. Okay, so what I told you now is if A is 2, and B is 0, and C is minus 1/60th, that is exactly q to the minus 1/60 times g. And similarly, if A is still 2, B is now 1, because it's now n squared plus n plus 11/60th, then these two are modular functions, which means roughly that they're components of the vector that behaves like that. I'm not going to go into anything technical. So Werner Naum asked, is this very common? Should we be not surprised? Maybe APC is just always a modular function. But no, he made a conjecture which was proved part of it by a student, this and the rest later by me, so I'll just say a fact. So it's a theorem, it takes some work, separate cases to prove it's not a deep theorem, that they're exactly, FAPC is modular, exactly, we know the complete list, and it's a list of 7 cases, of which I already gave you 2. I won't write them all down because it's 21 numbers. I'll just tell the A, it's either 2 or 1 or a half. And so there are 3 there are 2 triples with 2 that I gave you, also 2 with a half, and 3 with 1. So 2 plus 3 plus 2 is 7. But they've been known, all of those 7 had been known for a long time. But he guessed, and his student proved partially, and student proved the case would be a 0, not the full case, that this is the short finite list. So, okay, now you know that whatever this is, it's very rare. Why should we care? Werner Naum actually made a more general thing. So instead of this, I'm now going to take A to be not a rational number, but an R by R matrix. But it should be a symmetric positive definite matrix. So if R is 1, it's just a number. And similarly, B will be a vector now, and C will be a vector, a number. So we have an R by R symmetric matrix, a vector of length R and a number, and now I do the same thing, but now I have n1 up to nr, all greater than or equal to 0. Here I take the product of these 2 factorials, and so I gave you one way. Take a closed 3-manifold, triangulate it, and let the xi's be the cross ratios of the vertices of the tetrahedron. Then you get such an element. But here there's a much easier way that Naum discovered that nobody had seen before. In the Naum equation, I'll first write abstractly, you have a vector. So it will be a priori C to the R, it's vector length R, but in the second will become algebraic. And the condition is that 1 minus x is equal to x to the power a. But x is a vector, a is a matrix, and I'm working multiplicatively. So what I mean by this is that for each I, 1 minus xi is the product of the j of xj to the power aij. So this matrix is some aij. Okay, so that's the Naum matrix. And now, what do we do? Well, if it's positive definite, which is our case, this is a unique solution. You can show that it's an easy lemma. Unique solution where the x, every xi is in the interval between 0 and 1. So they're all real numbers, all positive numbers between 0 and 1. So now, associate now to A, the classic psi thing, is the sum of this unique solution of the xi's. And now it's even easier to build a calculation I showed you before. If I compute d of x, it's the sum over I of xi wedge 1 minus xi, because that's the definition of d. But 1 minus xi by the Nine equation is the product over j of xj to the aij. But since we're working with f cross, the product becomes the sum, and remember that the wedge product is antisymmetric, this becomes a double sum over I and j of aij. I mean, x to the a in multiplicative group is a times x. So it's just aij times xi wedge xj. And this is clearly 0 because aij is symmetric and xi wedge xj is antisymmetric. So if you combine ij and ji, everything cancels in pairs. So it's a ridiculously easy way to make elements in this block group, but they don't have to be torsion. There's no reason. It's not the phi-term relation. And the phi-term relation is a special case. And so you get this, and so now the conjecture makes sense. We have this psi of A, and I say it should be torsion. But I can even tell you why. You see, if ABC is modular, then what does that mean? It means that if I take Z, and I have this vector of which one term will be FABC of e to the 2 pi iz, and then some more terms, this will be invariant under -1 over Z up to some matrix. So what it means is that if I take Q now to be e to the 2 pi I times -1 over Z, then this will be a combination of these unknown coefficients. It will be a power series in the new Q, e to the 2 pi Z, which means it will start with the leading coefficient. So what that tells you is that if you look at FABC, not of Q, that's called little FABC, which is f of Z is capital F of e to the 2 pi Z. I have to always make this change of variables. If I look at this function where Z is very small, I times epsilon, then you can send epsilon to I over epsilon, right? And so this one will correspond to, if I take Q to be e to the minus epsilon, that means that the Z will be I epsilon divided by 2 pi, actually, because e to the 2 pi iz is epsilon. So it's slightly more complicated. If Q is very near 1, I'm going in the unit circle. I'm tending to 1, I'm at 1 minus epsilon. That corresponds to height 1 over Z. But now, because this is modular, Z is the same as 1 over Z for some other functions. So when I send Z to 1 over Z, it becomes 2 pi over epsilon times I. That's the Z prime. And so that gives me a Q prime to e to the 2 pi Z prime, which is therefore -4 pi squared over epsilon. But every modular function has an expansion with rational powers. So this has to start up to lower order terms. It has to be 4 pi squared over epsilon times a rational number. But when you compute what this is for any A, B, and C, just real numbers, it's an easy computation. That this thing is e to the some constant over epsilon plus O of 1 actually. And this constant, remember we had the Rotterdam of L. You take L of 1 minus L of xi. I goes from 1 to R. And so that's the formula. That's an easy fact. But now L of 1 is pi squared over 6, so this is pi squared over 6 times R. And this is L of our element xi, which was the sum of the xi. So if this thing is a rational multiple of pi squared, this is a rational multiple of pi squared. Now this is a rational multiple of pi squared. But remember that L went from the block group to R modulo pi squared Z. So to have a rational multiple of pi squared means that the image is torsion. So probably the element is torsion. So that's the reason for this conjecture. If it has any chance to be modular, then the thing you get has to have dilogants, which are rational multiples times pi squared. But the only natural way with that is if you start with torsion. So that was the conjecture, which I said is now a theorem.
I'm sorry, there was R before.
Sorry?
So now you have L, and before you had R.
Oh, sorry. L is for left and R is for right. In Japanese, it's the same. Sometimes I call it R for rod, and sometimes L for logarithm. So thank you very much, it's R. But R equals L. Okay.
So may I ask one question about the theorem? So are you saying that if your A is good, so the condition is satisfied, that you can find...
No.
No.
I'm not. I'm saying...
No, I understand. So suppose your A is good.
I'm not, and I said, let me finish the lecture, I'll go and ask questions after. I said that the converse is a huge open question. I'm not saying the converse. I'm saying what I wrote. If FABC is modular, then A is this
Yeah, I
property.
understand. But at least can you find B and C?
No, I said, if I can do this after the lecture, it's the biggest open question in the field, but it's a very good question that I want to get. Actually, the lecture that I want to give starts now, and I have 5 minutes left. So give me a little chance to at least tell where I was wanting to go, because I now see that that I won't really get there. So now I want to talk about 3 manifolds. Actually, I'll talk about knots. So a knot might be, I can't ever draw it, but the simplest knot, the simplest non-trivial knot is this called a figure 8 knot, which looks like this, and then you can never do it, but anyway, some people can do this. Something like that, that's called the figure 8. And then if you have a knot, K, then it gives the 3 manifold, which is the complement of the knot, in free space. And in this case, that has a hyperbolic structure, and for almost all knots, according to Thurston's ideas and Caroline's theorem, it's hyperbolic. So we pick one which is hyperbolic, and then we know that the abstract topological structure fixes everything. It fixes the geometry. Now, to a knot, there are many invariants, and there are particular quantum invariants, and they're kind of semi-classical, and then completely quantum invariants. The semi-classical invariants I want to mention are the Jones polynomials, which are actually polynomials in Q or Q inverse. And then there's a generalization called the colored James polynomial, just more write N is a natural number. If N is true, it's the original one that Jones first found. So that's a kind of a classical invariant. These are just polynomials. So if you fix like N7, that's an interesting polynomial with a lot of coefficients, roughly N squared coefficients, and they're all not invariants. But those are kind of semi-classical. It's a finite list. But then there's something completely different. If N is a natural number, there's an invariant classically called the knot. It's not N, it's called the Kashaev invariant. Kashaev defined it a completely different way, but Murakami and Murakami showed that this is the same as you take the nth Jones polynomial for that same n and you evaluate it at the standard nth period. So it's completely explicit. It's going to be some element of z of zeta n for each n. Of course, it's a different polynomial each time. So it's something completely explicit, and for instance, for the figure 8 knot, which I will call 4-1 because that's what it's called, the Jones polynomial, I won't write it yet. Okay, now comes the interesting thing. If I take the Jones polynomial, and let me fix Q to be zeta 300. So it's a 300th root of unity very near to ground. I pick that 300th root. And then I look at the values of these semi-classical ones. So if I look at this, if n is 1 up to 299, then this thing is bounded, it never gets beyond 25. But if n is 300, then Jn is roughly 5 times 10 to the 45th. So there's completely different behavior. And this is a true quantum invariant. And that's by this theorem, that's the Kashaev invariant. And by the way, you can show rather easily that if you take Jn of an n, capital N to the unit, this has period n. Capital N. So if n goes n plus capital N, it repeats. So here, the first 300 values were very small. Then one is very big, and then the next are again very small, the next is very big, but it's the same one. If you want, you can interpolate backwards. I'd like to do that, we call this J0. Response to periodic. You can speak of J0. So J0 is now a function which goes from the rational numbers into 2 lines, or into C. And now you saw that this number is something very, very big. The Kashaev invariant, unlike the other ones, is exponentially small. And that's the famous volume conjecture, which is now about 25 years old, also due to Kashaev. And the conjecture for any knot, but it's true for the figure 8 knot, but for any knot, this Kashaev invariant, so I'll just call it J0 of Zn, or Kashaev invariant, should be E, it should be exponentially big, and that exponential, figure out what my notes were. These conjectures actually go much further.
Is it the exact equality or is it asymptotical?
Oh, sorry, plus little again, sorry, asymptotic thinking. So I was going to say, let's take the case before 1 now. We know exactly how it looks. It is J0 invariant. By Anderson and a student of his found the leading terms the power of 3 over the 4 over 3 times this constant times n. This is the volume, which doesn't matter here. But then both I and Garofalidis with colleagues independently found the complete asymptotic expansion. Well, I mean, complete asymptotic expansion. So it's a power series in 1 over n, multiplying this exponential term with the power series. If you write it as a power series in pi over n, or better, pi over n squared 3, actually is rational coefficients with some output to q. But if we take a general note, then there's a much longer story which I'm going to have to skip about the conjecture I found on the computer, and then now we've checked with Garofalidis for many cases. We've actually proved it for this slot, which is some modularity property of these things that I'm not going to enter. But let me just say the leading term here will always be n to the 3 halves times e to the cn. That's the part that was known before. But then there's a full asymptotic expansion, something like 2 pi I over n to the j. And these aj will be algebraic numbers. But actually, this is kind of the boring version. The interesting version is you make the function on the rational numbers. And this sends x to the same j0 of e to the 2 pi ix. Because remember, to see modularity, you can't work with q. You must work with x, where q is e to the 2 pi x. And then it turns out that the right way to see this, so this is about j of 1 over n. But actually, it's about any modular. J of x plus b over cx plus in the modularity conjecture says that this j function behaves like a modular form. That is, I have talked about that way 3 halves times the same volume over 2 pi times x plus d over c, times some product of aj amounts 2 pi I over cx plus d. So you get a whole bunch of power series, aj of alpha, where alpha is, let's say, d over c. So it's some rational number. So we get infinitely many power series, which conjecturally all belong to Q bar. That was discovered independently by me and with 3 other people, Sergei Krukov and Dimoftin and Lennels, and also by Garofalidis and Tang. But then later, doing very explicit calculations, sorry, they only had this conjecture for the original, this one. This one was something I found, this modularity. Then I did a lot of calculations alone and made with Garofalidis. And something amazing happened, and I'll just tell the story in words. So we get, now forget all these details, we have some black box called knots. So a knot, and an algebraic number. Well, the knot already gave us a field, remember, number field, which is the one we discussed before, the trace field. But we also are now getting a bunch of power series, phi alpha of epsilon, with coefficients which are algebraic numbers. And you can compute these coefficients by some interpolation method numerically to very high precision, 200 digits. It's not at all obvious. It's easy enough to compute the left-hand side, but then you have to interpolate to find the coefficients to high precision. But there's a way to do that. And now something amazing happens. The full conjecture is this, and I'll just say the main line in a few words, and the main theorem. So we have this for the knot, we have the k and this rational number alpha, we have the power series. And so let's say alpha, well, alpha was d over c, so it's a c root of unity. So we have the associated root of unity, e to the 2 pi I alpha, which is the c root of unity. So let's put fc is what you get by adjoining cyclotomic extension. The conjecture is not that this power series has coefficients in that. But it does up to a constant. And that constant is something the computer showed us, and it's the cth root of a unit in the same field Fc. So this power series up to a cth root of a unit has coefficients which are all in this fixed number field. Now, so that is, as I say, completely experimental. We found this in the first case I did. The C was 5. This number had degree 20. It took a lot of work on the computer to recognize it. We did hundreds of digits. But it turned out to be the fifth root of the unit times some complicated number in that field. Okay. So now, I had to conjecture, because of this slogan, remember, the obstruction to modularity is the element K theory. I've also told that the knot, or any manifold, but in particular a knot, which gives a 3-manifold, gives you an element K theory in the block model. So my conjecture was that if this whole thing would only depend on that. I had that conjecture for 10 years. It was my dream. I spoke about it in many places. It meant if you have two different knots, which are completely different but have the same class of K theory, then this power series would be the same. After 10 years, we were able to compute cases. It's very complicated. The dream was wrong. But after the computer told us that this thing factored, it turned out this unit did only depend on the class of K theory. So in all examples, if you took two knots with the same class in K theory, then the factor in front, this prefactor, was the same. And so that suggested, as a guess, just because it used numerical things, but that was the theorem of the same authors I said before, of which the other turned out to be a corollary after some work. The theorem is that there's a canonical map. I'm simplifying a little, but let's say C is a large prime, something like that, from the block group of F, modulo C, into the units of the field when you take the cyclotomic extension, and then again modulo C powers. And it's actually, we know the exact image at some eigenspace. So we have a canonical isomorphism with something, and we have two proofs of this, two versions with the block group and the K theory. They're completely different proofs, and although the groups are abstractly the same, we don't know how to relate the two proofs. So there are two constructions. So just to end, the amazing thing is this is a theorem of pure algebraic number theory. You start with something very abstract, which is an element in the K theory of the number field, and you construct a unit. But remember, I told you at the beginning, you cannot expect to construct a unit even in F, let alone FC, which is more general, an actual unit. But luckily, we aren't saying that, because when this thing is unique, it's only unique up to C power. If I change this unit by C power, I can absorb it into this. So it's only unique, and that you are allowed to do. And it's a very beautiful, it's a one-line construction. Afterwards, somebody else, I can show them privately. It's a very simple formula. But the point I wanted to emphasize, this is a theorem, not a conjecture, of pure number theory. But it was motivated and discovered by something that's completely conjectural from a different field of knot theory and from computer experiments. But those computer experiments told us that this unit was there, and because of the slogan relating K theory and knot theory, this should be true. It was true in the experiments. After 5 years of work, it is a theorem, and then this as a corollary implies, I told you, not Nun's conjecture if you combine this with some information about the asymptotics of themselves. So that's the story I wanted to tell. I'm sorry I ran a little over. So thank you.
Questions?
Now all questions are legitimate, of course.
You made a big deal about Jn and zeta n having zeta n being very, very close to 1. What happened?
Oh no, sorry, it isn't. I mean, zeta n is very close to n in the original calculation. Actually, that's my main contribution to this whole field is that all of the topologists and all of the mathematical physicists until 10 or 15 years ago, they were talking about Q groups. When you talk about Q groups, quantum groups, you sometimes specialize for roots of unity. But in the asymptotic forms, Q always went to 1. And I said, let's let Q to be any rational number. So exactly, the original Kashaiten variant is J, and this is exponentially big. So it's a constant, which is the volume times n. But if you look at J on the unit circle, it's just some function. And actually, let me give you draw a picture. So here, well, let me do it in x. Remember, J of x is this J0 function of e to the 2 pi hours. Now, if I do it at 0, it's 10 to the 45, it's impossible to draw. And so you take your log of J. And so I have a picture, I have it right here. If someone wants to look at it, you probably can't see it from where you sit, but that's what it looks like. So I'll draw it. It looks like there's kind of a cloud of points, and then it's got a little bit of structure and another cloud. Anyway, it's kind of a black picture. What you would expect? This is x. This is just some random function for the rational numbers. The graph is just black after a certain height. But when I made a graph of the log of j of minus 1 of x divided by j of x, like that picture here too is called draw it. It has a few jumps, but it's a curve. A few points, well, all rational points to be honest. It jumps, but the jump is very small if the denominator is big, so you have more or less a curve. So that is the modularity, that if you apply minus 1 over x or any modular transformation, the ratio of these two clouds goes away. So the whole point of this modularity is don't just look at the neighborhood of 0. So 1 over n, here's 1 over n, which corresponds to zeta n. But the whole point. On the other hand, it's not a new invariant, because since this is a polynomial, any root of unity is some number, the L divided by n, which is prime to n. That's just zeta n to the L, where L is prime to n. And that's a gamma of worthless sigma L of zeta n. Then, of course, the Jones polynomial of this thing, which my new definition would be j of the rational number L of n. By Galois invariance, it's just sigma L of the Cauchy invariant. So algebraically, you don't gain anything. You just need one of them. But it's complex numbers, they have very different structures. So that's if you think of it, that's the key question I want to say. It's important to get away from that special one near 0. We want the whole rational numbers. And then suddenly this modularity springs, you actually can't miss it if you draw this picture. Well, it's a modular function. This is not some theoretical belief, it was something that the computer discovered. Now I can try to answer your question. So the question before was in Nahm's conjecture, which I haven't even erased. It said that if for some triple ABC, FABC is modular, then this class psi A has to be torsion. Now there's actually a funny story, if you like mean stories about the speaker. There was a version of Nahm's conjecture, and two students of mine, well, one was an ex-postdoc and one was an ex-student of mine, both of which have been here often, wrote a paper saying, I don't know if it was in the title, but Nahm's conjecture is wrong. They gave a counterexample. But actually, they gave a counterexample to a strengthened formulation that I gave in my expository paper. I made Nahm's conjecture much better known than it was. I wrote a big survey paper where it was made a big point, and so many mathematicians heard about it. And I tried to make a guess what is the right statement the other way. And I made a guess that's too strong. But it wasn't his case. He just said there should be some connection both ways. So I went out on a limb, I made a guess. And they found a counterexample. Now the story against me is not that I made a mistake, that happens all the time. But that the counterexample they didn't find by looking at the paper. They looked at my paper. I'd given a long table of examples. And one of my examples was a counterexample to my own little conjecture statement. They hadn't rejected, so that was a little embarrassing. Well, that's under time pressure, I was very late. So, and that statement said, you see, I talked about this real solution, but Nahm's equation has many solutions. It's R equations and R unknowns. So it's a finite, each solution is an R tuple of algebraic numbers. So it's a zero-dimensional variety, it has many points, usually finitely many. The Galois group acts. So if you have one of the solutions and it gives 0 in K theory, so is the Galois orbit. But you could have several Galois orbits. And so I gave one example where Nahm's conjecture is true. It was, the real solution gave 0 in torsion, but they didn't all. And it wasn't one in that case. So I said the converse cannot be just a straight converse. I mean, anyway, there's no converse because I said B and C. You could say that if psi A is torsion, there exists B and C. But I gave an example where it wasn't. This real solution of Nahm's equation was torsion, but it was not modular. But then there were other orbits there, and they weren't torsion. So I said the correct conjecture should be if and only if all of the classes are torsion, all of the orbits. But in fact, I've given an example in my own paper where the special, the real solution was torsion. Some of the others were, but some weren't. But it was modular. So the answer is we don't know the quantity. you must have that the real orbit is torsion. It should be enough, we still all conjecture that the version I said is still true. If all of the orbits are torsion, there exists G and C. But nobody knows how to do it. And my request to, in particular, some of you who share one of the following two properties, but it's an intersection. Either you're very, very smart, which applies to a lot of people here, or you're an expert in vertex operator algorithms, which applies to quite a few others, with a big intersection, then maybe you can solve this problem. Conjecturally, you can guess using information about how the special cases come from vertex operators. Make a guess. What are the B, the C you can forget? But what is the B? Given A, how do you find the good B? And nobody has a guess. So we don't even have a conjectural statement the other way. And that's the big problem I've been trying for 10 years to make a good guess. I haven't found it. So there's a very, very interesting question of what should be the converse. And we don't have any idea. But at least the one I said is wrong. That's the only thing we know for sure.
Is it true that the relation between the knots and the units was used in the proof of your theorem, but it was just a motivation?
Completely true. How could it be used since everything about knots, first of all, not every unit has to do anything with a knot. This theorem is for all number fields and all C. Not every number field comes from a knot, and if it does, it comes from many knots. But much worse, the statement about knots is completely conjectural, except for the figure 8 knot where we proved it. So it's completely conjectural. It's a double, triple, 100,000-fold conjectural because not only we don't know that the numbers are algebraic, we don't know that they exist. We cannot prove that there's any asymptotic expansion. On the computer we find one. We find the coefficients, they're algebraic, they have all of these properties. But each stage of that is conjectural. So even if you knew everything, and we don't know any of these statements, but no, it was only motivation that suggested that there is some mysterious source of units, but the only thing you could see, if you forgot the manifold, was the classic K theory. So what I asked Caligari was, can you define a class? And it was at a conference in Oberwolfa, and within a week, he had found a way to make the class not in the block group that took much longer with the K theory. And then he had the abstract of our paper, then it was just him and me, correspondence came later. The abstract was one line. It said, we conjecture the equality of two numbers, one of which we cannot compute, and the other we cannot define. And it was exactly that. The number comes from equality you can compute to 100 digits. But you cannot define it, you cannot show it exists. It's a conjecture, but you can compute it. The other one is defined in algebraic K theory, and that one you cannot compute at all. But it's well defined, and that one you show K per unit. But later, we found a way, the three of us, to do it in block proof, not in K theory. And then you could compute it and define it, and so we had an actual theorem.
And then the question is, are there any applications of this relation between knots and units? Real applications, not just motivation.
Well, first of all, in checking that this is true at all, it's amazingly useful. So for instance, last week, I did extensive computations for all C, every prime C up to 100 for the figure 8 knot. And we found 10 or 20 coefficients of the expansion, numerically on the computer with very high precision, to test. But the only way we could do that is we knew what unit to remove. Because let's say the C is 17, so not a big prime. Then you start with the field F with some degree. In that case, it's degree 2. It might be degree 5. Then you adjoin the C third of unity. It's now 2 times C. But then 2 times C minus 1. And then you take the C through. It now is a huge degree. You cannot recognize numbers of that size. But now we know this unit a priori. If you divide by it, then the conjecture, so there is a conjecture now for knots, of course, that it's the same unit. So if we take the unit from the theorem of Caligari, and take that unit here and divide by it, that's so now the new conjecture that this thing divided by this unit given by the theorem, now it's coefficients of the simple field. So it's a much stronger conjecture. And those coefficients are now new. This invariant is known, so we can forget it. But the coefficients of this are now new invariants. So we get an infinite collection of not invariants, but don't be infinite, because C can be anything, and all coefficients of the power series. So we get a doubly infinite series. The constant term of this expands to zero. The top term is the so-called Rademacher proportions. That's a famous invariant. But all the other invariants are new. So we get a lot of new invariants, but they're only conjectural invariants because we can certainly divide this by this unit. But then we can only conjecture that the coefficients exist and are in the number field. So that they're conjectural units, but they're not visible conjectural units, so you can use them to distinguish knots. So that's a kind of an application in knot theory. And also the num thing was the num sums we didn't expect, but then it turned out when you compute for a num sums FABC, the asymptotics at any rational point, not at 1 over n, then you get the same unit. We can show that. And that's why, if it's modular, there are only finitely many limits, because all of the rational points are equivalent. And then you get just finitely many things, so extortions, like the theorem with the trivial unit. So, I mean, so it had applications to this famous conjecture phenomenon to new Golden variance. It's only 2 years old, and it could be more applications. It's getting late. No?
Is there any relation of the story to the Dana variant of hyperbola? Or
I
the
think so.
variant?
I used to know well how the Damon variant worked. I think the Damon variant can be used. So remember I said that the variant first in K theory. And so the K theory, so if F is the field associated with the knot, and the knot is produced by the side K, the block group. But then I have, wait, I'm answering. We can map into B of C in R two different ways, but we can also map into B of R in R one different ways. These coefficients are given by the Ploffino, and these are given by the broadest dipole, which I call R later, L-X. This one is the volume, and this one is essentially the Damon variant with the angle around the thing, I think, but I'm not an expert. So I think the Damon variant only, but I'm not an expert, I've forgotten even the definition. I think that only has to do with the invariant in the block group with this map from manifolds of knots to the block group, and then the realization of that by the dialog map into the reals and the complexes. So that's been known for a long time. The new input is the thing that goes beyond that. If I have in particular 2 knots with the same class here, so I take the difference, then this part is gone. Now what can I say? That's what these new invariants are, units and so on. So it's kind of the next level. So I think it's not directly related, but in the sense that it's one level higher. I think the Damon variant has to do with this term. Because the Damon variant is something with the angle around the thing, but the angle is only modular 2 pi. Remember, this thing mapped into R modular pi squared. There's a twist, but I'm not pi. So I think the Damon variant is there. I think people want to go home. Oh?
We know that this group on the right parameterizes cyclic extensions of FC on degree C. So
which group on which right?
that factor group, UFC modulo UF to the power C. So this theorem
It parameterizes what?
cyclic extensions of FC of degree C, because FC has ZC. Yeah.
Well, no, all of that. These are only units.
What?
This is only units. So these
F.
are, well, so it parameterizes some.
Oh, that's units, not all F, but the number field.
No, these are units of FC, but still it's units. It's not arbitrary numbers. If I want, you're talking about Kubrick extensions. If I have a field which contains the C-word FC, and I take any cyclic C extension by Kubrick theory, you join the C theory of some element of the field. But the field has infinite rank, but the units is finite rank. This is a tiny part
So
of
this
all
is
the
the unit
fields.
in number field.
No, it's the units in this
In
field. In this
sorry,
field.
the ring of integers.
It's the unit of the field FC.
Of the ring of integers, yes.
No, I mean, we're talking about the field. The original field was F, but the new field is FC.
Yeah.
So that's now my ground field, but the join to C through the unit. And now we have here, and we have the units.
All right.
We have the units.
Yeah.
And if you take any element of FC cross, anything, then you can adjoin to FC, the C through the X, that's a cyclic extension, and that's most general. But here we're only taking the C through of UFC. So it's very special. It's essentially the ones that are unramified.
So the answer, which extensions are going to be produced?
Well, that's not the original. That's a standard algebraic number there. I'm not sure I'll say it correctly. It's roughly unramified extensions.
Which extensions? Well, it turns out that the ball group allows to produce extensions of F, some extensions using that.
Yeah, I guess you could think of it that way. Actually, people have asked me that before. I'm sure that you can. So it's certainly given this unit, let's call it eta, I can adjoin the C through the unit. FC, doesn't matter which group.
Yeah.
And this is an extension, it's a cyclic extension by combination. And so we have certain extensions, and I think there may be another way to define them from K theory, it's not so easy from them. So I don't know exactly the precise question, but I'm not an algebraic number theorist, this was kind of an accidental side thing. I don't know the interpretation in terms of classical language of K theory. I think it's...
Okay, so let's thank the speaker.
Yeah. If anyone wants to see the picture, it's lying here. It's very cute.